All right, so I'll start this today and get this going, and this is what we'll discuss on Friday. All right, so we've alluded to learning theory a lot when talking about VC dimension. Maybe you've been exposed to VC dimension in learning theory. I think part of this is also to point out, one thing great about randomized algorithms is that it touches on all parts of computer science. So here's something that's like a little bit out there from where we started. We started talking about quicksort and stuff. But there's going to be some connective tissue because of the randomized techniques. So I really like that. I really like this idea that all these topics aren't so different. So, okay, we don't need to do this. Yeah, so normally I would review what we did last time, but we just did last time. So what we want to talk about is just basically all of these implications in learning theory that are coming out of just random sampling phenomena. So I guess today we'll just get it warmed up a little bit, probably just talk about what we mean by consistency model. Maybe we'll introduce the PAC learning model, but we'll see. Okay. So I made the same mistake last year. I made a slide thinking I would think of an example, and I just never filled it in. So, okay. So in the I don't know. I mean, I think it's not so hard to look around. But so in this quote unquote consistency model, you're given some space of examples, and for simplicity, you're just labeling true or false, 0 or 1. Okay? And a concept is any assignment of labels. Right? These are all just names. And a concept class is a set of labelings. Okay? And the basic question is, okay, if X is labeled by some unknown function, unknown label, but you know the concept class, then could you find the unknown concept from the labeled subset of data? Right? So maybe I don't know, what's the simplest example you can think of? Okay, so take dogs and bagels. So maybe one is okay, imagine you're on the line and then you're just looking at things that split the space in half, right? That was supposed to be in yellow. Okay. So you're only looking at concepts that divide the line into two sides, right? So your concept class is, there's some threshold, everything above a threshold is true, below a threshold is false or something, right? Like the melting point of water or something. What would be an out? Yeah. No, concept in general is any labeling. Yeah. And then usually what you do is as a prior, you say, if I'm assuming that the labeling is of some restricted family, such as I have points on a line and I'm only looking at labelings induced by a threshold. Okay. So what would be an algorithm to find a good concept? So if I just gave you the points and the colors and you were promised that it was induced by a threshold, what would be a good algorithm? A binary search, right? You just look for the last green point, the first yellow point, or something like this. Okay, so that's sort of the general goal in this consistency model. And actually, it's a little bit more interesting because you're given some subset of data, and you want to figure out the true label of all the data and stuff like that. So a little bit more involved. Right, so I think I'll at least be able to motivate PAC learning today, and then we'll pick up again. So given a training set of data, so X is your input, Y is your label, okay? Your goal is to find some kind of concept class that agrees on all the labels. Okay? So, or decide there is none. Which of course, if it's binary search, that's very easy, but maybe it could be more complicated. So take this one, disjunctions, right? So you can only write equations of the form A or B or C or not D or E or something. And here's a table of 5 samples. So this is a relatively small machine learning problem. What would be a disjunction that satisfies this? It's not a disjunction. So any formula like up at the top. Can anyone guess or come up with a disjunction that agrees? It's just ors. Disjunction. Uh, Survey says there may be more than one answer, but this is one I came up with, I guess. Okay, so you'll see that the things that are not x2 or not x5, uh, yeah, that would be consistent with these labels. Okay. Can anyone think of an algorithm? Can anyone think of an algorithm to come up with a disjunction systematically that's faster than brute force? It's not randomized either. Because you want to find a disjunction, silly. What would be like a greedy algorithm? Yeah, you can go through and say, should I include x1, right? Or not x1. And if either of them works, just take it. And take it, right? And and that will output something that's consistent. Or if you don't come out with anything that works, then it's impossible. Um, oh, right. So you can include zj if xi1 is equal to 0 whenever y is equal to 0. Otherwise, this kind of greedy thing is not so hard to see. And you can show your formula might be too big. It might label too many things to be true. Whatever is a true concept class will be a subset of this. Okay. But the algorithm is consistent. That's obviously a fast algorithm. And it'll give you something consistent. I'm a little over time. Here's one more. I think I'm very close to finishing though. Suppose you're doing rectangles in the plane. How would you do this? How would you come up with, so concept classes are all rectangles. Yes, this comes up every year, yeah. Yeah, you can find like the leftmost red point, rightmost red point, right? At some level, you have several choices. You could take sort of the biggest rectangle containing it or smallest. At some level, it's not clear which one you should do. You just know the concept class is somewhere in between. Okay. Uh, so yeah, you know, that might be like points you don't see that are sort of sketched out there. So here's the point though. This consistency model, which, it sort of had just been clever combinatorial geometric problem, it doesn't say anything about whether your concept class C prime has anything to do with the true concept class C star, right? Especially outside of the training set. So that could easily lead to things like overfitting, right? Like that disjunction algorithm we had, where you just add everything you can, right? That seems a little bit lopsided. It also seems like, in this kind of situation here, it's you don't know should you take the tightest rectangle or the biggest rectangle. If you assume that the points were, yeah, it's just not clear, right? So the point I'll end at today is that this model is like a nice first pass at trying to define what learning is, but it's just not subtle enough, right? It's not paying any attention to data outside the data set. So that's going to motivate certain randomized definitions of learning next time. Okay? All right. Thanks, guys. Okay, so we'll continue what we did last time, started last time. I feel like even with the short class, we're not going to use up all the time. I'm a little bit concerned, but then I thought of a great way to use class time at the end, if time permits. I'm going to leave that as a surprise. Could it be the turn-off bound proof? It seems like it would be good to touch on this before the midterm. Okay, so it's sort of sort of two lectures that are sort of connected. One is this geometric focused lecture about epsilon samples and epsilon nets for these kind of simple combinatorial systems. And then we also introduced the additive turn-off bound, epsilon nets, epsilon samples, all this stuff, right? You can get epsilon sample, you preserve the kind of the weight up to an additive epsilon, was 1 over epsilon squared. If you want the hitting set version in epsilon net, you only need 1 epsilon in the denominator. Okay, so this is what we started last time. And we're just kind of discussing learning theory and stuff like this. So today's discussion is not like super technical. Like I'm not going to give any like super like crazy algorithm like scooping balls out of points and some crazy metric embedding or something. It's really more conceptual. Okay, and it's just like, okay, now that we're a little more comfortable with probability, discussing it and stuff, how would we use that to try to imagine a definition for learning? I mean, by now you guys are probably very exposed to it because this is more trendy than ever, but it's still an interesting question that we can try to revisit from as if from a blank slate. So to recap what we did last time, so a starting point, a very natural starting point that you might come up with before taking this class might be something like a consistency model. So, you have some domain X, and then sort of the things that assign true or false, they're called concepts. Okay? And the basic problem is, okay, so there's some secret concept hidden from you that's labeling these points. Can you figure out the concept? Especially if I only give you a subset of the points, right? So a simple example, okay, so yeah. So the best thing an algorithm can do, okay, so it's going to take as input some set of training, labeled things, and it'll just try to find some concept that makes no mistake. So I guess this is not a name I came up with, but a consistent learning algorithm is one that can do this. Okay. Sometimes there's a question of, yeah. And in principle, it should be reasonably efficient. So a question might be like this. Your input would be the table with a square around it. We did this last time. And you want to try to guess this, or at least something that matches the table. And there is sort of a greedy algorithm that you can do. Okay. So just by, so if I look at like the first feature and say, okay, if the feature is always 0, when we output 0, I should include that feature positively and otherwise include negatively. And so you're just trying to add as much as you want that doesn't violate the table, or as much as you can. And then you can show that, okay, maybe you don't get the true formula, but the true formula will be a subset of this. Okay. And that's, okay, so you get some kind of consistent algorithm. Another example that we did together was just points in a plane where the family of concept classes are rectangles, right? And you have two, you could output the smallest or the largest rectangle or anything in between. And that will properly label things, right? So you just have to find the leftmost point, rightmost point, this kind of thing. If they were axis aligned, if it wasn't, okay, you have to figure out a little more geometry, but you get the idea. Okay. So this is certainly reasonable, this kind of model, but still, and they present, reasonable algorithmic questions, but you still might ask, is this really what we think of as learning? Right? Because somehow our model our model just says, oh, find something that matches the input data. It doesn't really say anything about the true label. Okay, so that's like the basic conceptual thing to overcome. Okay. So, well, maybe you all know this already, but so we're going to discuss one approach, a commonly adopted notion to address this. But I wanted to leave this blank, especially for those who haven't already taken a class on this, to maybe suggest possible ways to extend the model to make it more, you know, similar to what you might intuitively think of as learning. So up at the top are all the things from the consistency model. There might have some domain, you might have some concept labeling thing, but we want to come up with a new definition of learning, or a better definition of learning. Okay, well, we will change. We'll like kind of make the problem slightly more general. So first, okay, that was just both at once. Um, we're going to do two things. We are going to first allow the algorithms to output something a little different than the underlying concept classes. So you might have some data that are labeled by something, but your algorithm can only output rectangular classifiers or something like this, right? So we'll have a different family that we call hypotheses. These are also a structured family of labelings that the algorithm outputs. It's possible that it's equal to the underlying concept class, maybe it's not. Okay. And we're going to assume that the points are drawn from a fixed distribution, okay, which was something that didn't enter the model before. Yeah. So this is just making the model a little bit more general. Uh, well, in real life, uh, you may come up with an algorithm that ultimately is finite and kind of limited. And say for simplicity, it only outputs rectangular classifiers. It takes point sets and tries to find the best fit rectangle. And you want to run that algorithm even if the underlying data wasn't actually given by rectangle, maybe just rectangle plus plus, something similar to a rectangle. So rectangle is a good approximation, right? So we're just allowing a little bit of separation, okay? And ultimately to allow for, yeah, so that's the point. So this is, yeah, it's kind of a minor thing. It's not required to be, yeah, but I think and that's probably my intuition most of the time. Usually the concept class is some vague, unknown, abstract thing, right? So, but the hypothesis class is something very concrete because it's what my algorithm's doing. So at the very least, it always feels more concrete and specific to me, but that's just my impression. Okay, so I guess towards also another relaxation we're going to do is, okay, maybe this will be more motivating in a second. Okay, okay, so okay, why do we need the last 2 points? So if you're going to output things that aren't necessarily the true concept, if there's a difference between the concept class and the hypothesis class, then you're necessarily going to have some error, right? Because you're just not even doing the exact same thing. So for that, we'll fix some distribution of the underlying points, and then we can quantify the error, just say, oh, I choose a random point from this distribution, and okay, what are the odds that I get it right? What are the odds I get it wrong? It's very natural, right? Okay, so we haven't really done too much yet, but we've allowed some measure of error, which sort of didn't exist in the old model. The old model was like, there's something that was classified in a simple way, figure out a simple way to classify them, right? And now this is already a little bit more robust than before, right? We're not trying to get perfect algorithms necessarily. Okay, maybe this next part's more interesting. Okay, So with these parts in place, my challenge to you is to define a learning algorithm. How would you like quantify this is a good algorithm? You could use epsilon delta because it's already there, but you don't have to, right? But even just speaking out loud, how would you, your algorithm takes some probably labeled data distributed from X. We know it outputs a hypothesis. Okay, it should output a hypothesis where the error is small. That's reasonable. Okay, so we'll do that. Okay, so that's what we have so far. Uh, so M should be something modest. I don't know. Um, and I ultimately want to output a hypothesis where the error is small. That sounds quite reasonable, right? You give me the error parameter, can you get the error down to 10%? Oh, do you know? Well, so imagine you're doing a linear classifier. That means you're in a high dimensional space and you basically draw a hyperplane and this and that, right? So and you're just working with an algorithm that can only do this. So your hypothesis class will be these linear separations. So that may be known. That's just like what your algorithm can do. But whatever you do output, you're hoping that your, linear classifier has small error. That's reasonable, right? Now, so this is a very natural model, exactly what's up here now. But okay, so it's saying, okay, what's one flaw, or what's one, yeah, yeah, okay. So yes, so you're only going to be able to do something on this, and you're hoping it's going to capture everything. And okay, so if I told you that, can you make me an algorithm that takes input and always outputs a hypothesis with error at most epsilon? So one issue is like, what if your input data is terrible, right? What if like, I don't know, you were given, this kind of instance, except you only got blue points, right? Like, you would have no idea what to do. As soon as we start sampling input data, you can't really guarantee you're going to do something correct because this could happen with non-zero probability, right? So, so a really key point about this model, which I think, it seems so simple that, but really I think a really important conceptual contribution is to say, okay, I'm going to also give you some parameter delta, and you should be able to output a good hypothesis most of the time, assuming the input data comes from this distribution. So input data comes from a distribution and your testing or your true errors with respect to the same distribution. Okay? So you probably learn, you probably output a hypothesis with small error, but you don't have to always. And at the very least, that permits some error caused by the data that you sample from. Your algorithm may also be randomized and have some chance of error. But at the very least, it'll, without that, this seems kind of impossible, right? To say, oh, I can always, because the data itself might be terrible. Okay. Yeah. Okay. So yeah, this is a little bit more secondary, but this would be pretty good if you can get to be polynomial 1 over epsilon, 1 over delta. Um, so this might be a little bit arbitrary. I think at the time, well, it still seems reasonable. Like if you have to use 2 to the 1 over epsilon, then maybe it's not. You basically just want this to be small. You want m to be as small as possible to guarantee epsilon with some delta. And we've sort of decided, oh, a reasonable threshold is anything that's polynomial in 1 over epsilon and 1 over delta. In fact, I think we're going to get, today, everything will be polynomial in epsilon and logarithmic in 1 over delta. But there's no hypothesis that there's no guarantee that this hypothesis exists. Yeah. Right, right. So it's possible that your algorithm cannot learn this distribution. So if your algorithm is only trying to do rectangular things and your data doesn't at all look rectangular, it is impossible for your algorithm to learn this. Sure. So I think it's a learning algorithm for a particular distribution and thing, and you want to know if I mean you have an algorithm, you want to know if it's a learning algorithm for this distribution, this concept class, and the answer may just be no. So the question is not does there exist any fast or kind of efficient learning algorithm for this distribution. Um, I mean, for example, one could argue like, oh, the algorithm that so like a not very interesting algorithm that you want to exclude from consideration is an algorithm that loops over all possible concept classes and tests each one. Yeah. But yeah, so anyway, it's a model. But really what this sets up is a framework in which you start trying to develop algorithms or start trying to develop some theory of learning, right? Like, and now we talk about like learning in AI all the time, but this is, a different time when it was a little bit more theoretical. And at the very least, it puts together a framework, uh, that's somewhat rigorous, right? And you can start actually saying, oh, this idea is better than another because the M here is smaller than the M here or something. Okay. There's also an interesting thing that now the real thing we want to address though is the first point, which is that your algorithm is working on some training data and it'll maybe get some good empirical error or something, which is to say error just on these labeled points. That doesn't guarantee that you have good error here. Okay, so we're going to study those conditions. And that gives you a general, that's what we call a generalization, right? Oh, you study some special cases, would generalize, right? In my algorithms class, if you memorize all the answers to the homeworks, well, you'll be able to solve a new problem on the exam, right? So yeah, usually not. Okay, it's really more a comment of my teaching than anything. Okay, so so as an example, right? Um, when you're trying to understand how big M needs to be, okay? So if, let's say our algorithm for the rectangular case, let's say that C and H are both the rectangles. I can think of two natural algorithms. Give me the smallest rectangle containing the positive points, or give me the biggest rectangle containing the positive points. Okay. And if it's here, your error is sort of this region. If it's here, your error is this region, right? Now, to even quantify what I mean by error, we have to assume some distribution, right? So we can make this argument more precise by saying, okay, let's say I have a uniform distribution over like a 0, 1 by 0, 1 square. Okay. Now, let's say that my algorithm is going to choose the smallest rectangle. So my error is this margin between the red and the yellow, kind of uniform. Then you can start trying to calculate, okay, how many samples do I need until I can guarantee that the kind of space between the smallest rectangle and the true rectangle, represents only an epsilon fraction of the distribution, right? So you can say, oh, I need to make sure that these margins are actually small enough. So I need to hit all these margins inside the true concept class, right? So some epsilon fraction of this, epsilon fraction of this. You need to get those margins small enough to guarantee the error is small, right? And those are just geometric regions. And so you can actually start to calculate really as a function of epsilon, how many samples you need. Okay, so this will be probably 1 over epsilon squared or something. Okay. But now you can see, okay, you have the boundary conditions to actually just crunch out this number. It's just a calculation at this point. Okay. Um, okay. So let's talk about generalization. So let's say that you have, so a consistent algorithm, again, is one that will output a classifier that agrees with all the training data. Okay. So Now we go back to this question of, okay, if you have if you're good on your training data, are you good in general? Okay, generalization. So, so that's, so let's look at this. Suppose we have a finite hypothesis class. So this is our first case, simplest case. Okay. And you have an algorithm that can always output a consistent hypothesis. Maybe you're guaranteed the concept class is rectangles and you're outputting rectangles. You can always find a rectangle that works. Okay. So the claim is that this, for a finite, if you have at least log of the number of hypotheses divided by epsilon, then with probability at least 1 minus delta, any consistent hypothesis has error at most epsilon. Okay, so a consistent hypothesis means it's correct on the training data. So if you have m input points. So a corollary is that for the finite hypothesis setting, a consistent learning algorithm like the disjunctions and rectangles we've done, well, maybe disjunctions, would give you this more subtle learning algorithm we just discussed. Yeah. Oh, okay. Not raising your hand. Okay. All right. Okay. Why is this true? Chernoff? Okay. If you applied, how would you apply Chernoff? Uh, yeah. Okay. So maybe we'll fix H. So 1, if H is correct on Xi, 0 otherwise. Actually, do we want to do it this way? So you're working within a so your choices of hypothesis in this setting is limited. It's finite. So we have the size of the hypothesis class. So what we want to say is that if I have a learning algorithm that can only choose a finite number of hypotheses, okay, whether or not that's realistic, we'll do more general versions than this in a moment. This is the first one. Size of this script h, log size of h. Okay. So actually, I think what we might want to do is we might want to, instead of doing correct, count the number of incorrect. Okay. Now, okay, so yeah, okay, so I fix h and I have these indicator variables, and maybe I have m of them, one for one training sample. What do I do next? How do I connect this together? Yeah. Okay, so let's take a step back. Now, what I want to show ultimately, okay, so for this thing to be, so I want to show that if a hypothesis has very large error, bigger than epsilon, then it should make a mistake on the training set, right? Because then our algorithm would not output that hypothesis. So we want to fix h such that error of h is at least epsilon, okay? Okay, good. Okay, so now what's the expected value of these xi's? They're each at least epsilon. So if you add them together, stop it, should be at least epsilon m, right? And if you want to apply concentration to this, then epsilon m should be at least how much? How big does like the average need to be for some of these things to start kicking in? Uh, yeah, or maybe it'll be easier if I wrote it like this over m is greater than or equal to epsilon, right? Okay, so if I apply additive Chernoff, just following the thing in the box, the probability that this thing is equal to 0, okay, is at most the probability that it's an epsilon factor less than the expected average. I'll write mu, where mu is something at least epsilon, right? So this thing is less than or equal to e to the minus 2 epsilon squared m. So if I want to union bound, if I want to get this to be small and union bound over all of the hypotheses, what should I make m? Yeah, it should be log of m needs to be, there's means epsilon squared in denominator to cancel this out. And I need log of hypothesis to take a union bound over the hypothesis. And then we have this delta, so it should be log of. So actually, it's very close to what we want, except it's epsilon squared instead of epsilon. So what did we do wrong? So additive Chernoff didn't work. This bound is stronger than what Chernoff gives. So what are we missing? Well, okay. So this implies that okay. So this would imply that m needs to be at least, if m is at least log of h divided by delta over epsilon squared, then this is less than or equal to delta over all the hypotheses. If you can see, that's size of h. I know it looks like any other letter. Um, and that's enough to take a union bound over all the hypotheses. That's that's why we'll have the h over delta. That part's actually correct. The problem is that this epsilon squared is too weak. Yeah, yeah. So the sampling is coming from the true distribution. So what do we do wrong? Yeah, you can do the multiplicative version and say that's actually not quite it. That's not where the issue is. In fact, maybe as a hint, what we did is much more sophisticated than the actual way to analyze this. Yeah. Ah, okay, so this is simple. Is that also what you have in mind? Okay, so this thing, every time I get a sample, it's going to make a mistake with probably at least epsilon. It's called 10%, right? So the first data sample comes in. If it's correct, it survives. If it's wrong, it dies. They all have to be correct for us to be misled, because this is a consistent learner. So we're asking it to be perfect. So it's more like count min or something, right? So we just need one of the samples to point out that it's not perfect, and then we'll be good. Okay? So that looks more like this kind of calculation, which looks more like 1 minus epsilon to the m, because you have 90% chance of killing it off, 90% 90% chance of it surviving, 90% of it surviving, 90% of it surviving. It could be smaller, but it's at most this. And you want this to be at most delta over the number of hypotheses, so that you can say, okay, I take the union bound over all the hypotheses and the overall error probability is delta. Okay. So then you're going to put, e to the negative m, and you're going to say, okay, m should be at least log of this divided by epsilon, and then that's how you'll get your bound. Okay, so yeah, so consistent learner actually is simpler. Fortunately, I think you guys have, okay, well, let me see. So this kind of problem here would be an example that this applies to. Okay, because for disjunctions like this, there's actually only a limited number of hypotheses you can pick, like 2 to the n or something. Okay, if there's n variables. Well, maybe that sounds like a lot, but still, we have a consistent learning algorithm for this, right? So it wasn't, well, maybe it's a little tricky, but you can come up with an algorithm that on a particular subset of data will label everything correctly. And we just want to know, oh, this formula, which might be too big, how well does it generalize, assuming the input comes from a distribution? And, okay, so for disjunctions, how big is the hypothesis class? I guess 3 to the n? Oh, I didn't write anything. Okay, so I guess each variable you can include positive, negative, or leave it out. 3 to the n. So if you take a log of that, okay, you need n samples or so from the underlying distribution, n over epsilon, to guarantee epsilon error. You want 1% error, you need 100 n samples. Okay. All right, good. So that's okay. All right, so what you guys have actually did a good job for. Okay, so a different kind of thing is you can say, okay, I have an algorithm that's not consistent. It doesn't output perfect things, but outputs things with small errors. Will that generalize? Okay, so if I have a sample S, I'll write error sub S to be the error just on that sample. Okay. So anyone want to guess what this should be? So this is a little bit different, right? So how many samples do you need for a finite hypothesis class to guarantee that for all hypotheses, your empirical error will be within an epsilon additive of the true error? Yeah? This time it's going to be epsilon squared. Okay? So this is what comes from additive Chernoff. Okay? So I won't do the proof because we just did it for the wrong problem. Okay? Okay, good. We'll keep going. I guess I'll start going faster. Okay, so so why are some people interested, or why is finite hypothesis class like even interesting or something, right? So one justification we always give is something called Occam's razor, which you might have heard before, but keep it simple is basically the idea. Does anyone know who the big Aristotle is? No one? No. Any guesses? Fun guesses? No. Oh, so I should mention that I mean, this framework is done by Leslie Valiant. That's Paul's dad. Yeah, who's done a lot. He'll come up more times in this class. Um, no, Big Aristotle is Shaquille O'Neal. He's like one of his many nicknames, and I think like they kept giving Kobe the ball, and he's just like, just give me the ball. Don't get like, I'm 7'5" and 400 pounds. Okay. All right. So, okay. So one way to bound the hypothesis class is to just say how many bits does it take to write it down, right? Because everything's running on a computer, so there's something finite already about it. And Occam's razors kind of suggest like, oh, the fewer bits, the more likely. So you might want to choose algorithms that have kind of small descriptive complexity of the hypotheses, right? So, okay, so here are the two theorems, but I want to restate them in terms of the number of bits used to describe any hypothesis. So what would M become for the first one to guarantee that all consistent hypotheses have real error at most epsilon? In terms of B, if B is the number of bits. Okay, so log of number of hypothesis becomes B. Okay, and this will be the same thing with epsilon squared. Okay, so I don't know. I mean, this is all kind of us trying to grasp at what does learning mean, trying to put some math around it. It's a reasonable framework. All right, let me give another fun one. So we can look at some of the stuff we did last week. This is why I put one lecture after the other. So for a particular hypothesis, I can say, oh, what are the shapes induced by the things labeled true, right? And maybe that has small VC dimension. Like if it is rectangles that has small VC dimension. If it is circles, hyperplanes. That's actually quite common, right? So if the hypothesis class is a simple geometry as defined by growth, parameterized by growth, which could be a stand-in for VC dimension, can you get better bounds? Right? This is practical, and this was sort of asked implicitly when we discussed, why we even studied this stuff a few times ago. So this is just to remind you, but hopefully you still remember. Last time we showed these epsilon nets and epsilon samples. So epsilon sample means you're within an epsilon additive error. Epsilon net means you hit anything with measure at least epsilon. Okay. So, okay. So we're going to try to get the same theorems again. One, okay, so suppose the hypothesis class has this growth. Okay. Claim, if M is at least something, then with probability 1 minus delta, all consistent hypotheses have error at most epsilon. So what should M be? G of n means that over any n points, the limited set of shapes you have can only define g to the n subsets. So if you had disks in the plane, you can only actually do n cubed different subsets because the VC dimension was 3. Or because if you think about it, if you have points kind of a disk capturing some points and others, you can kind of shrink it until it runs into 3 points. So the 3 points would kind of define a whole equivalence class of circles as far as which points they contain. So the fact that this is much less than 2 to the n gave us the stronger samplings. Yeah, something like, yeah. So this is going to be, but how many epsilons? Yeah, so we're just going to plug in the epsilon net theorem directly. Okay, so the epsilon net theorem actually maps directly to generalization when the classifier induces a small shape. Okay, I'm brushing over a little bit of technicality, but it's okay. Um, so what you kind of want to do is you want to look at the shapes induced by both positive and also the negatives. So it's like anything that's inside a circle or anything outside a circle, right? But that's just adding the complement. That doesn't actually increase the VC dimension. So it's kind of okay. Um, the other one, uh, this one is sort of this uniform learning. So I want to argue that my error is at most epsilon off. So this way, if I output a shape with small error, I know my true error is similar, right? So what would this be? Okay, so this will just be the epsilon sample theorem. Okay. But this was very exciting because many of the algorithms that we were naturally doing, like linear classifiers, um, in fact, was sort of an infinite size hypothesis class, right? Because you could put the hyperplane anywhere. Yeah, but the input is a continuous distribution of points. Uh, uh, but also, even if there was n points, right? This says g of 2m, which is like d for the VC dimension d, right, is independent of the input size. So even if there's many points and you want to argue, oh, there's only hyperplanes induced by 2 points at a time, log of this will give you log of the number of points in your input set. And this is actually independent of the number of points in the input set, which also plays nice with a more machine learning framework where you have a distribution of points that could be anywhere, things like this, right? So this was a very strong argument for the algorithms that we don't use so much anymore, but it was a very compelling argument. Yeah, yeah. So what we did last time was so if g of n is any polynomial, okay, then this is going to look like this is going to be a d log 1 over delta. Yeah, so you can just solve it for how big does m need to be, and you'll find that choosing d log 1 over delta over epsilon squared is fine, is enough. So if you're doing disks in a plane, d is 3. So you really need log 1 over delta over epsilon squared. If you're doing hyperplanes in d dimensions, d is d. Okay, well, um, as usual, uh, we'll just have to do this next time. Well done. We postponed it again. So yeah, that means I probably won't put it on the exam.